All right, I'll start with the first graph here. Okay, so limit as x approaches -8. So anytime we want to see if a limit exists, we have to start with finding points on both sides of -8, close to -8. Okay, so here's -8. I find points on both sides of -8, and I follow the path towards -8 along where the graph leads me. And they're both going down to -infinity. We know that there's a vertical asymptote, which means our limit doesn't exist. So we say D and E, but we have a subcategory because the arrows are headed in the same direction. Okay, G of -8. G of -8, we want to see, is there any point that lives at -8? We don't see any point that is defined here. So none, undefined, D and E, one of those. All right, part C, limit as x approaches -5. So again, if a limit is going to exist, we have to be able to see some consistency from our arrows. So we'll pick points on both sides of -5. Then we draw our arrow towards -5. And we see the arrows are headed towards different directions, headed towards different y value. So, get it. This worksheet. Okay, I have an extra one up here. G of -5. We want to see, is there any point that lives on the graph when x is -5? So there's a hole there, there's a hole there. These are both undefined, but we do see a point here. So that point is defined at y equals 4. Okay, limit as x approaches 2. So anytime there's a limit statement, we got to look for our arrows, let the arrows guide us. So pick points on both sides of 2. Draw arrows towards 2. Do they agree? They do. They both are leading us towards a y value of 6. Right, G of 2 is this ordered pair here. 3 is a y value of 3. G of 7 is the graph going to have a y value at 7. We do see G of 7 being 2. And then limit as x approaches 7. We again pick points on both sides of 7. See if the arrows are in agreement. They are. Those both arrows are headed towards a y value of 2. Any questions, A through H? Okay, number 2. Sketch the graph with the following characteristics. So I'm just going to go down the list here. So limit as x approaches -5 equals -4. So I know that my graph is going to lead towards this y value, but I don't want to define that point just yet. So I like to start with an open circle at that point, and I like to extend in both directions to give it that limit being true statement. So let me find that order pair, -5, -4. I'm going to start off with whole. Extend my graph in both directions. Now, I know I've taken care of that region. Maybe I can extend it further after I find out more about where the graph is living. G of -5 is undefined, so I want there not to be any point defined, and the whole is part of undefined there, so that's good. There's nothing that I need to add. Just have to make sure I don't put anything at -5 at the end of by the end of the problem. So both are accounted for. It's already undefined, right? A whole is considered undefined.
So why would like look for the limit? Why is it? Why do you still get it?
Let's see. Ask that again.
Like if it was the limit of f of x equals actually like look at h. Like if there was a hole there, in the problem before, if there was a hole there, then like would we still give a number, or would it be undefined?
If there was a hole there, are you asking about the order pair or asking about the limit?
The limit.
The limit will still be defined like over here, right? The limit is still defined as long as the arrows are headed towards that direction, that value. So this limit does exist because if I pick points on either side, the arrows are going to lead me to that y value. But the point is undefined, which is what we want because it says g of -5 is undefined.
Just when I ask for a point, not a limit.
Yeah, when I ask for a point. So I like to always start off with a hole because there may be something else that's telling me to plot the point elsewhere.
And
you can, yeah. Okay. But I like to leave it open just because it's easier for me to fill in later rather than erase.
Okay.
That's my whole thing. Yeah.
But do you have to fill in?
You don't have to.
Okay.
Not if there's nothing that tells you to. Now, if this says g of -5 equals 8, then you have to fill in the hole at 8.
And it would still, if it said it's 8, it would still apply to A. Still be true.
It would still, yeah, A would still be true because the limit is still down here. Okay. Yeah. And then if it says g of -5 equals -4, then that will tell you, oh, I'm going to fill in that hole because now I know that hole is going to live there. Okay. Yeah. Okay, g of -2 equals -8. That's an order pair. Limit as x approaches -2 equals infinity. So that tells you that there's a vertical asymptote there, that as we approach -2, that our y value is going to shoot up to positive infinity, both sides. So we know there's a vertical asymptote. Our graph will look like this. Right. That infinity means I need both sets of arrows going up. So I think this is my preference. I think this makes the graph a little bit easier to sketch. Is if I see a positive infinity, I like to have the arrows further up on the graph rather than down here. It just makes it easier for me to connect with the rest of the graph. And then likewise, if I see negative infinity, I typically like to have my arrows down further towards the bottom of my graph. You don't have to, but it just makes it a little bit less awkward to connect with the rest of the graph. That's just my preference. So I don't want to do too much on beyond that asymptote, but I just want to, go far enough so I can at least fulfill that condition, and then I'll leave my graph to connect with the rest later. And make sure your arrows are moving closer towards the asymptote and not further away. Okay, g of 2 equals 7. That's an order pair. Okay, so now for part F, limit does not exist at x approaches 2. So you have a lot of options here. You can create another vertical asymptote. You can make the graph disconnected, like what I'm about to do. or you can make it an endpoint. So I'm going to purposely have two different destinations towards 2. I'm just going to pick a random y value and extend in the other direction. So a lot of different possibilities here. Everyone's part f can look different, and that could be fine. G of 5 equals 1. Limit as x approaches 5 equals -3. So I want my graph to move towards this y value of order pair 5, -3, but I like to do a hole here so that I'm not conflicting with something else. So I'm just extending my graph slightly. G of 7 equals -3. Limit as x approaches 7 is also -3. So I'm just going to extend my graph both directions. Okay, so I'm just going to clean up my graph a little bit, see if I can make my graph connected. You don't have to, I just prefer to see what I can do here.
Do you have to make some sense?
You don't have to, no. It makes it a little bit cleaner, I think.
Okay.
As long as each of these conditions are fulfilled and that you don't fail any vertical line test anywhere on the graph, you're good.
If you had left the defined point at 2, 7 without the hole below it, would it still be
Right here.
at 2, 5, sorry. Like you see how you have a, well, you didn't this time, look at mine. At 2, 2 at yours, the hole at 2, 2.
Yeah.
If you hadn't done that and you had like left the point at 2, 7, would it still be undefined? The point at 2.
Yeah, let me see what yours does.
Like I have it work how you did on your key, but like if I didn't have this and I only had that was, would this point still not have a point?
Yeah, it was still not even. If you want to just erase and show me what you're talking about, just like.
Okay. Yeah. It was just like,
Yeah, show me what.
if it was just like that, would that point be undefined but ask for?
That point is still defined,
Like if you
but
asked
the
for
limit.
Like you see on yours how you have a point at 2, 7.
Yeah.
Okay, if you didn't have the hole at 2, 2 with the point at 2, 7, like when you asked for the limit of 2, 7, would that still be undefined?
You mean if I didn't have this part?
Yeah,
Yeah, the limit will still be undefined.
okay.
Because I gotta have arrows from both sides headed towards this point, so.
Okay.
Endpoints, yeah, so endpoint is undefined. Differently, different sets of branches also undefined, and vertical asymptotes also undefined. Okay, any other questions before we move on to, yeah?
When you have the thing on the left, do you have to curve it like down to the left, or can you just curve it up?
This part here?
Yeah.
Yeah, you can make it go up. Yeah, there's nothing in this description that's telling us what's happening with the arrows, so you can let it go anywhere you want. But I do need to have some extension past that hole. Otherwise my limit's not gonna exist. But later on, after we get past this quiz, we are going to talk about end behavior, and there will be some descriptions that's going to guide what is happening with those arrows as we move out from view. Yeah.
No, right side to ask him to, if I didn't connect it to the blade and then just connect it to the hole, that'd be.
Cloud call.
Let me see. You have it.
Yeah. Just fixed it. So,
I can't do that because it said the limit doesn't exist there. So then you force the limit to exist there. I gotta have some disconnection there. Yeah.
You need us to put vertical asymptotes. Like, do we need?
What do you mean?
Like, you know, you're a VA, do we need to write a VA?
You don't have to, no, I just wanna show that, that's what this means. Whenever you see this notation equals infinity or equals negative infinity, that means there's vertical asymptote, and that's gonna help. Yeah, if you can subcategorize, I want you to subcategorize. So that just means if the arrows are going the same direction, that means you can say something. If they're not going the same direction, then you just leave it as deity. Okay, so we can go through our steps here. Common denominators. Sorry, before we do that, right? Show me that it falls under that 0/0 category before you commit to all the algebraic steps. Okay, so we know common denominator is going to be what's needed here. So my common denominator requires both the 6 and the x plus 6. Okay. If I compare my denominators, old denominator versus new denominator, my new denominator has an additional 6. So because of that change, I need to balance the numerator with that change as well. 6 times 1 is 6. And the second old denominator is missing an x plus 6. So I need to multiply the top by x plus 6. Okay, so now the whole point here is we can merge the two fractions now that we have common denominators. So I'm going to put the numerators together and distribute the negative through. So I'm going to go back to my problem now that I have this upper portion resolved. I'm going to put this in place of that top part. Okay, so the nice thing about all these algebraic problems is that you know what you're trying to what you're trying to get after, right? Whatever your denominator is showing you, you know that you're trying to find that match in the numerator. So you know you're looking for something along the lines of x, and we see that x begin to appear, and you know that these are what you're targeting because that's what you want to remove. Okay, but I'm going to do this here. I'm going to multiply by the reciprocal here, so I'll flip that x up to the top. Because there's always going to be a hole. I mean, if we see 0/0, you know there's a hole. You know there's something that is going to pair and cancel out. And you know that the x is obviously causing that 0 below. So there must be an x hiding above that's causing that 0 above as well. So I know that if I see that x show up, that's a good sign. I know that is what I'm eventually going to, cancel out. Okay, so the reciprocal of x is 1 over x. So there it is. I see clearly that these x's can reduce each other because I have one x in the numerator and one x in the denominator. So my remaining expression is this. Okay, so now I know my hole has been removed. I should no longer get a 0 over 0 when I reevaluate. So now replace the remaining x with 0. 0 plus 6 is 6. 6 times 6 is 36. Get negative 1 over 36. Okay. All right, number 4, what's the first thing that we do? Right, well, yeah. Yeah, let's see what happens, right? We don't want to assume it. Let's just go ahead and do direct substitution. So when I do that, what do I get in the numerator?
Um,
1 over 0. So that's not 0 over 0, right? This is telling us something different. What's happening here? What does that mean? Therefore, limit doesn't exist. Yeah. Yeah, you mean like arrows? Yeah, but we don't have to subcategorize with algebra problems yet because we haven't learned that yet.
Okay.
Right, but good question. Yeah. Yeah, but it's possible there's a subcategory, but I'm not going to require it. All right, number 5. First steps first. Here we do get 0 over 0, so that tells us that there's a hole. And the clear thing is that you see this x minus 5? That is what you're trying to get to show up above. You know the x minus 5 is obviously what's causing that 0, so there must be an x minus 5 hiding above. So as you're working through the problem, you know you're on the right track if eventually you get some x minus 5 to show up. Okay, but we know we got to go through our conjugate method here, so conjugate is a conjugate is a pair that looks almost like the original term, except the sign in between changes. So the conjugate of root x plus 3 will simply be root x minus 3. Sorry? It doesn't matter, right? Whatever two terms you have, the conjugate is simply the opposite sign. And the nice thing about a conjugate pair is that they will produce a nice term with the radicals removed. Yeah, if we FOIL out. Yeah. So if you look, right, even though the second term looks more complicated, the first term is 4, the second is that root x, sorry, that square root expression. And so the conjugate of this term would just be 4 plus that square root expression. All right, so let's FOIL the numerator out. First pair, we get 16. Second pair, we get the radical removed, just 11 plus x, but it's a negative times a positive, so we get a negative in return. So let's protect that second expression with a parentheses so that we don't forget about that negative distributing through. Okay, now we can distribute the negative through here. So 16 minus 11 minus x. Sixteen minus 11 is 5, so I get 5 minus x. So we're close, x minus 5 and 5 minus x, but are they the same? They're not the same, but we're still are able to do something to eventually get these canceled out. They're only different by what? -1. So I can just factor a -1 above. You don't have to show the step. If you don't want to, you can just cancel them out and just make sure that a -1 is going to as a leftover. So the x minus 5s cancel out. There's a -1 left over. And now the whole is removed. We should no longer have to worry about a 0 over 0. Now we're going to reevaluate into our reduced expression, and that'll lead us to our true limit. So 5 gets inserted for x. There's a -1 still above. So 11 plus 5 is 16. Root 16 is 4. 4 plus 4 is 8. So -1 over 8. Questions? Okay. All right, number 6. First things first, let's not assume anything. So direct substitution. What does direct substitution give us? Let's check though. We get 4 minus 1 minus 2 over 1 minus 3. Anything else we need to do? No, that's our limit, right? So if we get a real number, then there's no need to do any factoring, any reducing, because we already have our answer. But I think the tendency is sometimes we look at the problem and we think, oh, we know where this is going, and we end up going down the wrong path because we think that it's a hole. We're trying to find that hole, and we can't find that hole because it's already a real number. Okay, number 7. Let me let me give you a kind of a simplified version of this. I'll give you one maybe as messy as that. Okay, so we do go through direct substitution. We get 2 times 9, 18. 18 minus 15 is 3. 3 minus 3 is 0. So there's a hole. So we can go through our trinomial factoring. Multiplies to be -6, adds up to be -5, and we have to adjust for that coefficient in front. Okay, so we were looking for an x minus 3 in the numerator, and we found it. So we can remove. And then go through direct substitution and see that that should lead us to a real number now. So 3 times 2 is 6, 6 plus 1 is 7.
Like you did like a chart on your key. It was like a little.
Yeah, star method. No, but you can show, okay, even if you were trying to do your factoring method, we can't do that until the GCF is out. So once your GCF is out, then you can handle whichever factoring method you want to choose. But that 3 has to come out first.
Yeah, you just have to.
Yeah, so that's similar.
Either.
Good. Yeah, so
Okay.
that works. This is the star method. There's also a grouping method. So yeah, whichever method works for you, that's good. Just make sure your GCF is out. This case, there's no GCF, so you can go directly into that method they use.
Do whatever.
Yeah, you can do whatever. Yeah, you don't have to follow any one method. Okay, number 8. Okay, so number 8 is going to feel very much like number 5, maybe a little cleaner without that looking for x minus 5 there, but okay, so we get that 0 over 0 to show up. Identify the conjugate, expand out, and you know what you're trying to look for above, right? There's an x below, so there must be an x hiding above. So we're trying to get that x to show up. Eventually, when it does, you know that you're on the right track. Get those x's to go away. There's a 1 left over up top. Reevaluate, and then you're left with root 5 plus root 5. So careful, root 5 plus root 5 doesn't equal to 5. That, what you're thinking about there is be root 5 times root 5. Root 5 times root 5 is 5. But this is basically saying 1 root 5 plus 1 root 5 is 2 root 5. So think of it as you're adding like terms.
Squeeze method again.
Yeah. I'll do I'll do an example of that
Okay.
at the end.
Wait, you said the squeeze is on the.
It's on the quiz, yeah. But I'll do one that at the end to make sure that you guys are good. Okay. Let me show the steps for number 9. Number 9 should feel very much like number 3. Okay, so we first get that 0 over 0 to confirm us that there's a hole. Common denominator is going to be 2 and 2 minus x. We see that this 2 minus x is missing a 2, so we'll multiply the numerator by 2. This old denominator is missing a 2 minus x, so multiply the numerator by 2 minus x. Once we are sitting at common denominators, we're able to merge them into the same fraction. We can combine all the numerators together, add and subtract the numerators together. So distribute the negative through, we get 2 minus 2 plus x. So you're left with x over 2 times 2 minus x all over x, because this is now the updated, cleaned up version of this original top portion. And we see the x that's beginning to show above, so that's an indication that we're going along the right track. Dividing by x, the same thing as multiplying by the reciprocal, so I'm going to bring that x up as 1 over x. So I got this top portion, I got the reciprocal going, the x's match and pair up. Take those out, reevaluate, replace any remaining x with 0, and we're now able to arrive at a real number that we couldn't before the hole was removed. right, number 10. Limits x approaches 2. Again, there's a complex fraction here, but let's see what's happening at 2. So insert 2, and for x, we get 2 over 2 is 1, 1 minus 1 is 0, 2 minus 2 is 0. So really complex fractions. Okay, I'm going to focus my attention on this top portion there. 2 over x minus 1 over 1. My common denominator is just x. I can see that my denominator already matches, so I can just take the numerator, keep it. Here, my denominator is changing from 1 to an x, so I need to balance the numerator with an x as well. Merge those together. So this is now my updated top portion. So now that I have my updated top portion, I know I'm looking to see if that can pair up with the denominator in my original problem. And I'm beginning to see that there is a similarity there. So, but I'm going to try to get this out of a complex form here. I'm going to move that x minus 2 up as a reciprocal. It's a little bit easier to see that 2 minus x and x minus 2 are directly above each other, but they're not the same. So, but they're close. So what can I do? Yeah, factor a -1 now, or we can just cancel them out and just keep a -1 as a leftover. So once I factor -1 out, the -2 plus x and x minus 2, they're in a different order, but they're the same thing because the x's are both positive, the 2's are both negative. So the only thing left over is -1 over x. We reevaluate. Okay, any questions with those? Okay, let me do a squeeze theorem problem here. I'll do 2 of them.
That the inequalities that will always be.
Yeah, the inequality will always have 3 functions. Sorry, this one. Always have 3 functions. There's always 2 that are known, and then the middle one is unknown. What does the bottom one give us? 8. I do direct substitution. 10 minus 2 is 8. Direct substitution here. Also 8. So if this is gonna live between 8 and 8, this has to be what? Questions? Let me show you one that gives a different result.
You just substitute and then if they're the same, the middle is also gonna be eight.
Yeah.
Good morning, faculty. Just another reminder that NHS is providing breakfast for us and the teachers lounge on the main hall for staff only. Thanks so much. Have a good day.
Okay, what do we get here?
Well,
12, right? This is 12. Do we know what the limit is?
No.
No. We know it's between 12 and 18, but we can't pinpoint a number, so we say that it's inconclusive. So either we know or we don't know, depending on what the outer numbers give us. So starting, I think a couple of years ago, maybe like last year, year before, all the tests and quizzes are all 100 points.
Okay.
Yeah. So, but this is going to go under the quiz category, and then tests will go under test category, and then the homework will be, yeah, separate, 10% of the grade. Quizzes, I think, are like 35%, and the tests are like 50.
That's what you're writing. Just write it. Let's do it.
Questions on?
It'll be less than this review here. The front will be the same, more or less. And then there's 3 categories, right? So I'll give you one of each. Yeah. And then squeeze theorems. Yeah, squeeze theorem. Yeah, so I just did 2 examples here. This is one that works. This is one that doesn't work. So if it works, the outer numbers will be the same, which then you can make a decisive conclusion. If they're not the same, then you don't know what it is.
but does this work?